This is week 2. So class 2, right? So as before, what we'll do, I think, is an hour, like a roughly hour of lecture, a 10 or 15-minute break, and then a 45-minute, the rest of that hour, doing some problems. This time with Macaulay 2, if you have that available with you right now. Otherwise, there are some things to try to figure out as well. And you can work together, of course. And then after that, we'll continue. We're going to continue at the sort of the basic level at the moment that we've done. So I'm going to just be doing a little bit more Groebner stuff, applications of Groebner bases, and that's the plan. So today are Groebner bases and applications. And the main application, well, it's a whole lot of applications, is elimination theory, basically, elimination of variables. After break, though, I would like to start considering syzygies and free resolutions. And that will also include Groebner bases for modules and things like this, which in commutative algebra and algebraic geometry, we absolutely need all of the ability to do all this stuff for modules. So let's just recall last time. We had the division algorithm. I'm going to sort of state it. Okay, so this thing is equal to a monomial order, a global monomial order on R, which, as always in this, is going to be K of x1 to xn, where K is some field. Later on, if K is the integers or something else, we're going to want to deal with that too. But for the moment, we just deal with this, and then we figure out how to generalize it later. And we're going to let F yeah, I guess we'll do it this way. We're going to let F be an ordered list, and the FIs are not equal to 0, but they're in R. Okay, so they're non-zero polynomials in R, and it's an ordered list. And then for all G in R, there exists unique, and I'm going to say G1 to GR, and H in R. They're only unique because of the ordered part. Okay, so then there exists unique such that 3 things hold. The first one is the main thing, is that it really is a division. G1 plus F1 plus GR, FR plus H. That sum is equal to G. Well, one solution for this right away, if that was the only thing, where all the G's would be 0 and H would be equal to F, equal to G, that wouldn't be so useful. So then this one is that no term of H is divisible by the lead monomial of Fi for any I. Okay. So it's every term in here is not in the monomial ideal generated by these things. And then the third one is to get uniqueness, we can specify what the monomials we're allowed to use here are. And the way we can say that is no term of G sub I is divisible by any lead monomial of Fj. Well, for not all of them, but for j less than I. Okay, and this term here is really saying that when we do the division, we start with this. We take the very first Fi whose lead term divides it, and then we subtract off some multiple of that Fi, and that really is exactly this statement here. Yep.
Last time you wrote GI times leading monomial Fi.
That's what I meant to say also. Yeah, in fact, I have it here. No term of GI. Okay, I didn't say this very well. Let me get this better. Let me actually write what I have here. No term of GI times the lead monomial of Fi. Okay, that's what I had, right? Is divisible by any lead monomial of fj for j less than I. Is that what I had before? Okay, good. And then the notation that we had here, I don't know if we actually said this, but G//f, okay, the F is this ordered list, is going to equal, let's do it this way, G1 down to GR. Okay, that's in R to the R. It's a column vector. And G%F, which is going to be the same thing as the remainder of G with respect to F, is going to equal, what did I call it? H. Okay. And then, so what we have here is that G is equal to the vector, the matrix F1 to FR times the vector G1 to GR, which is this guy, plus the remainder. And that's the form. Okay. One way to think about these monomials is the following. To think of 2 and 3 is the following. Let's let delta 1, this is going to be the set of all multiples of the lead monomial of F1. So this is for all alpha. Okay. So that's exactly, no term is divisible by any lead monomial of earlier stuff. This would, if for other ones, this would be the earlier stuff, except for the first one. And then delta 2 is going to be the set of all x alpha times lead monomial of F2. But we get rid of delta 1. Okay. And then finally, delta R will be the same thing, x to the alpha lead monomial of FR alpha minus the union of all these other guys. And actually, that's not finally. The final one is delta. This is equal to the set of all x to the alphas, all monomials, minus the union of all of them. Okay. And so one way, I won't write this down maybe, but number 2 would just say that all the monomials are in delta bar of H. And then the other one would say that all the terms of GI times the lead, all the terms of GI would be, well, GI times that lead monomial in the corresponding one here. So this gives us a way of partitioning the thing. Now, one way that you oftentimes look at these things is via the following example is a good example, a reasonable example. Let's suppose that F1 is equal to x cubed plus some lower terms, okay? F2 is equal to xy plus some lower terms, and F3 is equal to y squared plus some lower terms. And we want to do a division with respect to this. So what are all these deltas then? This is the staircase. So this is going to be the exponent of I, of x. And this will be the exponent of y. And so it's 1, 2, 3. I'm just going to do it like this. Sometimes you do it as boxes. But so here's 0, 1, 2, 3. So x cubed is this guy right here. Xy is right here. This is 1, 2, 3. So that's x times y. And where is y squared? I guess it's right here. So what are all the monomials? The monomials in the lead monomial ideal are all of the monomials above this so-called staircase. Okay. So this is like the staircase. But what are the deltas in this case? Well, delta 1, F1 is this guy here. So delta 1 is all the monomials above that. So this is delta 1 here, which includes all the stuff on the boundary. Okay. Delta 2, so let's say that's delta 1. And in fact, maybe we even, this is probably a bad color to use. This is delta 1 in green. Okay, and now what about delta 2? Delta 2 is everything above this, except we excise all that stuff. So let's do that here. Here is delta 2, but not that outer stuff. So it goes to 1 before that, I guess. Here, but I'm not going to write it that way. Oops, shoot. I just broke my chalk. Woohoo. Oh well. Okay. So this is delta 2, basically. And then this is y squared, this is delta 3. And what are the monomials in delta bar? That's just this, and this. This is delta bar. Are these 4 monomials? Okay. So it's a way of partitioning all the monomials. And it turns out to if you want to actually do any sort of reasoning, not actually figuring out how to compute things necessarily, but proving things, this kind of topic is pretty good. Any questions about that? Yep.
Can you just restate what the interpretation of 2 and 3 was in terms of the delta?
Yeah, so 2 would say that all the terms of GI times that lead monomial of Fi are in delta I. Okay, and then 3, no, sorry, that's 3, and then 2 says that all the monomials of H are in delta bar. Does that make sense with everyone? If I need to write more down, you can ask me questions and I'll start doing it. But at the moment, I just want to give you an idea of this. It turns out that this is actually kind of cool the way it works out, because we'll be able to use that to prove computational syzygies in a little while, except that I probably won't go into that much detail about it. Okay, last time we also had defined a Groebner basis. So we fix R and then a monomial order on it. And remember, R is a polynomial ring over a field K at the moment, always. And we let I be contained in R be an ideal. And we had the lead monomial of I was equal to the monomial ideal, mon-ideal, of all lead terms of every element of I. Okay, and the definition for a Groebner basis is G. I think I used slightly different notation last time. G1 to GS is a Groebner basis of I with respect to the order if 2 things hold. A, each GI is in I for all I. And B, that the lead monomials of G1 of the Groebner basis guys is actually generates the lead monomials of I. Okay, so that was the whole concept of Groebner basis. And last time we also had defined, but I'm not going to go through that again, that I is G. So G is reduced or monic or minimal. We usually are interested in reduced, which just means all these GIs are monic. There are no extra generators necessary. There's no divisibility relation on these guys, and that you've really reduced all the elements so that you don't have anything in there. Okay, now at the moment, if I want to go over to that board, we have to switch this. Okay, cool. So let's do a very simple example. Let's suppose that G1 is equal to x squared minus y squared, and G2 is equal to xy minus 1. And let's let I be the ideal generator by these guys. And let's suppose that x is greater than y, and this is, say, the Lex order. Okay, is this a Groebner basis? is G equals G1 to G2 a Groebner basis of I? So we have two lead terms already here. We have x squared and we have xy. What if we had more ones, what would they have to be? They would have to be not divisible by one of these things. R here is just k of xy. Two variables. So the only lead terms that we might have are 1 or some multiple of y, some power of y. So do we have any such things? Well, there's a 1 in y squared over here, so maybe it's hard to tell. One way to do it, though, is the whole concept of S pairs, which is why we're doing this example. So if I can, so the and the solution here is the answer is going to be no, but we don't know that yet. So how do you uncover new terms? One way to do it is you take two of them and you multiply by things so that they cancel. And that turns out to be the way that it works for here, for the exterior algebra, for the vial algebra. All of these, all these cases, they all work in the same kind of way, or mostly they do. Okay, so here it's going to be, if I take y times x squared minus xy, and I subtract off x times xy minus 1, this is yx squared, this is yx squared, it's canceling the lead term, and what do I get? I get x minus y cubed if I did it correctly. This is a new lead term.
X squared minus y, not x squared minus y.
This is x squared minus y squared. Yeah, in fact, that's even what I have written down. So I don't know where I got that. Yeah. So x squared minus y squared, y times it, and if I just multiply it out, I get this. X is the lead term because it's Lex order. And is it in here? If it isn't, I can take the remainder with it. But in fact, it's not in there. So this is a new element. So this is going to be G3, and that's a new element. So it turns out, if you have to think about it, but G equals G1, G2, G3 is a Groebner basis. This is all possible lead terms. Actually, that's not true at all. That's not true at all. Okay, so I have it written down that it is. Awesome. So anyway, so what we have here is we do have these three things though. However, notice that this x minus y cubed divides these guys. So we can actually change these without changing the generating set. We have to be careful of that. But we can take this and reduce each by these things. And if you get that, you also find, well, this is just replacing x with y cubed, right? So if I plug in y cubed, I get, let's say G is a y to the 6 minus y squared. That's actually a new term, lead term. And if I plug in x here, I get y to the 4th minus 1. And then I also have this one, x minus y cubed. And if you think about it, these will include those in the ideal. Okay, so this is contained inside of I. Is it a Groebner basis? Well, I want you to think about it, but it is. This is a Groebner basis with respect to this order, but it's not a minimal Groebner basis because here we have, well, x is the lead term here, that's fine. Y to the 4th is the lead term and y to the 6th is the lead term, but y to the 6th is divisible y to the 4th. So in fact, a reduced Groebner basis of I is just given by either one, this y to the 4th minus 1 and x minus y cubed. Okay, so that's a Groebner basis. That really gives you all the possible lead terms. You need to check. You have to make sure, like this is saying that all the lead terms are anything in x or anything with at least a 4, y to the 4th. It's still, we don't have the theorem down that says that this is a Groebner basis yet. So, but anyway, that's what it is. But it is such a thing. Okay, so in a bit we will say something about computing, giving an algorithm for this. But first, I want to do the following proposition, which was this all was done in Buchberger's thesis in the 1960s. But G is a Groebner basis for I with respect to some order this. WRT is just with respect to in my world. Okay, so so this is the case if and only if the remainder of F with respect to G, and I guess G is ordered here. I've ordered it here. In fact, actually, it turns out not to matter on the ordering, that this is equal to 0 for all F in R. No, for all F in I. This you should think about the proof, but it's really the division algorithm. Suppose it is a Groebner basis for I, and I take the remainder. What could it possibly have? If I take the remainder, I'm supposed to get a new monomial that's not divisible by any of the ones I've already got. But that's supposed to be everything in the ideal. And so that if I'm going to leave this proof is do this as an exercise, if you haven't done it before. You'll get more out of it than if I just repeat some little thing up at the board. Okay, but this is kind of cool, except it's really useless, actually, in some ways. Okay, it's actually nice to show that if you have a Groebner basis, you can just get that these are 0. But otherwise, you have to go through an infinite number of elements before you can do that. So that's not a very useful feature. Here, though, is a really important observation. Okay. If it's a proposition, I guess, if G is a Groebner basis for I under or with respect to, let's use the same notation, with respect to this, then G generates I. In other words, everything in I is just a R linear combination of things in G. This is really a useful statement, as it turns out, because oftentimes we can prove that something's a Groebner basis, and if it's if it's a Groebner basis, then it has to generate. So that's going to be the one way we find things. Like even for finding things like I intersect J, we can find a Groebner basis of it maybe. And then actually that one's not a good example. But anyway, we can find a Groebner basis, and we want to know if it generates, because we really want a generating set of that thing. We don't really care about Groebner bases as such. But this will give it. So how does the proof of this go? Well, if it's a Groebner basis for I, then the remainder of every element is 0. So let's let F be an element in I, and that the remainder of F with respect to G equals 0 implies that F is equal to, okay, I've changed notation from over there. These are G's now. Let's say that G is equal to G1 to GR, or GS maybe. So I have two things going on here notation wise, and we're going to have to be flexible about it because we have not enough characters around. Sometimes I want to consider a set like F over there might be just a set of polynomials or a generating set, or I might want it to be a Groebner basis. I like G's for Groebner basis just because of the G in there. So oftentimes I'll use this thing as that. And maybe I actually take this to be an ordered set too, because we haven't proved yet that it matters, that it doesn't matter for a Groebner basis. But if F is equal to the remainder is 0, so what does that mean? That means that there exists H1 up to HS in R such that the following holds, that this is equal to H1 times G1 plus HS times GS. Okay, does that make sense? But that's in the ideal generated by G, which is what we wanted to show. So it's really a straightforward fact, but it's hard to stress how useful that is. Okay. Any questions about this stuff so far? Am I sort of going through this in an okay clip, for instance? Okay, we're going to just talk a little bit about computing Groebner bases now. So let's talk about computing Groebner bases, GBs. Okay, let's see, I need more since I broke my chalk. So situation, R is equal to K of X1 to Xn as usual. This is a monomial order. And let's say I is equal to a bunch of elements F1 to FR. This is an ideal inside of R. And say all the FIs are not equal to 0 for all I. Just so we don't have to worry about that. Okay. So the idea is how to compute a Groebner basis for I. And actually, let's give it a name. We'll call it G. Okay. There's a number of things that we can do here, but the basic idea is that we are going to use. Where's my example? We're going to use these kinds of operations. So the idea is to compute that, or the plan is to do that. And the idea is to cancel lead terms. So here's a definition. So if F and G are in R are non-zero, let's suppose that F is equal to C times X to the alpha plus lower terms. So this monomial here is the lead monomial, and this is the lead term when you throw in the constant. And so C here is in the field. And G, say, is equal to D times X to the beta plus lower terms. And D is also in K. Okay. So those are the lead monomials or terms of F and G. And the definition is the S polynomial. Okay, S stands for syzygy, although I don't know if that's actually what it really stood for at the beginning of the whole game of FG. By definition, is just going to be the thing that we just did over there to cancel these guys. So what is that? This is going to be D times some monomial, which I'll have to say, times F, minus C times some monomial times G. What should the monomials be? Somehow we want to go up to the least common multiple of these things, right? So it's really the least common multiple divided by that thing. There's another way of writing that down. So we want this to be the minimal one that cancels. Okay. So one way to write it is we had defined last time is that if I take the smallest monomial that when X to the alpha I get divisible by X to the beta, that would be X to the beta colon X to the alpha. Okay. Do you remember this notation? This is for monomials, this is pretty easy. This is just X to the xi to the beta I minus alpha I if it's greater than or equal to 0. Otherwise, it doesn't have that variable in it. And then this is x to the alpha colon beta, x to the beta. So the point is that x to the beta colon x to the alpha times x to the alpha is equal to x to the alpha colon x to the beta times x to the beta. This is not necessarily the case if these are just, I don't know, if these are just polynomials or something, but for monomials, this kind of thing works. So is this okay? I could write this down as LCM divided by that, but I like the colon things better. So remember what this is. Well, anyway, so this is the S polynomial right here. It cancels it. And then, so this is, so various people had discovered Groebner bases before, not Groebner. Groebner was one of the people that sort of discovered it as well, before Buchberger's thesis. But in fact, they didn't show how to compute them at all. They just used some of the features of it without naming it. But what he did was he figured out how to actually compute these things. Okay, so what is it? So here's the theorem of Buchberger. Is that G equals G1 to GR, GS, say that set is contained in I, is a Groebner basis for I. All of this stuff depends on the monomial order. So if I change it, everything changes. So I'm not going to write that down here, but it's sort of understood. This is if and only if for every I and J, and in fact, if we want, we can choose it to be, since it's going to be the same for I, J, and J, I, we only have to take one of those. If I take the S pair, S polynomial of GI and GJ, and I take the remainder of that with respect to my set G. I guess I made it ordered here, but if I take this, then I get 0. Well, these things, notice, are in the ideal I, because F and G, if F and G are in the ideal I, which the GI and GJ are. So this thing is in I, and if it is a Groebner basis, this will reduce to 0. So this thing being a Groebner basis implies this side easily. So so note, this one is trivial. But why is it that if you take these specific little guy, this small number of things here, that if those all reduce to 0, then you've got the whole Groebner basis? That needs proof. And we're not going to prove that right now. So this needs proof. And we might, we'll say something about how it goes, but not until later. Okay. On the other hand, exercise, you should do this on the previous example. So I said that over here, oops, actually, can everyone see me? You moved it back. Okay, thank you. Way over on the other board, we had that we had that I said that this was a Groebner basis up there. You need to actually now prove it. Yes. No. Actually, it turns out not. Because if it is a Groebner basis, they will generate. So you do not need to assume that they generate. What? That's a good question. It would seem that way, because if I just took 2 of the polynomials here, Yeah, that's right, exactly. Okay, so in this needs proof and why don't I say and yeah, and G is equal to I. Okay, on that side. For instance, or a one element set. I mean, yeah, whatever you do. So we have to have that statement in there somehow. If we somehow show that something is a Groebner basis for some other reason, then we do not have to do that. But you're absolutely right. That was a good call. Okay. Anyway, so try that on the previous example. But this gives us an algorithm now. And so I just want to write down that algorithm. So the algorithm is the following. So let's let G equal the set, the list F1 up to FR. This is our generating set. So I is equal to the F1 to FR. And I guess I'm assuming they're all non-zero. So I'm letting that be my initial set. There's all sorts of ways of improving this. And I'll say something about that in a second. Okay, let this be the case, and let S be equal to the set of all pairs I and J. Or maybe I is less than J. Sorry, what? Yeah, I do. So in fact, we're gonna let GI equal FI for I less than or equal to R. Okay, and then we're gonna add in GIs after this point. Yep.
So the round brackets around the G.
Yeah, it's really it's an annoyance of trying to be careful. I would like this to be just a list, but the way I've defined the division algorithm, I need it ordered. So I'm going to just keep it ordered this way. And actually, to tell you the truth, this is not a bad way to do it in general. Okay, so this is the set of all pairs. I guess I should maybe say where they go. So they're all the possible pairs on these R elements. 1 to R. Okay. Okay, and now while S is not equal to the empty set, okay, as long as I have a pair in here, this is keeping track of this is my to-do list of what pairs I have to compute. I want to do the following. I'm going to take I comma J is going to be remove one element from S. Yes. Okay. No. F1 to FR, FIs are in R. Okay. The FI, and then I'm going to set, I'm just going to define G1 equal to F1 up to GR equal to FR. I don't really need to do that. There's other ways of doing it, but I'm just going to start my Groebner basis with these guys, and then I'm going to add more stuff into it. They're the generators of I, and they're non-zero.
Are they minimal?
No, I don't care if they're minimal or not. This is not going to give me a minimal one. This is going to give me some Groebner basis, and then I have to make it minimal. A Groebner basis has no minimality assumption. It's only the reduced Groebner basis or the minimal Groebner basis that is. Yep.
So you're saying we have a list of generators given for the ideal. Let's initialize the variable G to be this list.
Exactly.
And
But
then we'll modify it as we go.
that's right. So what's going to happen here is, yeah, so this is a computer program, right? So I'm going to, and it's an imperative one, not a functional one. So I'm going to take this, and I'm going to initialize G with the list of the polynomials I have already, and then I'm going to modify that list as I go. And but in fact, the only way I'm going to modify it is adding new things at the end. I'm not going to actually modify those polynomials. Now, in reality, that's not the way I would do it. But for this this first algorithm, that works out pretty well. So remove one element from S. So I take it and then I actually make S smaller. I can do any one of them if I want. And now I let H be equal to the remainder of the S polynomial of that guy of I comma j of G sub I and G sub j. Okay, at the moment, they're just those guys there. And we take the remainder with respect to the set G that we currently have. Okay. Now, there are two options. If if the remainder is equal to 0, then that went to 0, and that's awesome. Then we don't have to do anything else. So in fact, I'm just going to say if H is not equal to 0, then what do we do? Well, then this thing didn't reduce to 0. However, if I add H in, this is in the ideal after all, if I add it in, then the remainder with respect to that would, if I put it at the end, the way it works is I will get this first, and then I would reduce with respect to that, and I get 0. So what I want to do here then is append H to G. Okay. And then also I want S is going to equal, and say that H is equal to G sub S now, G sub L. Okay. So it's whatever the size of that set was. So say H is equal to G sub L now, because it's the Lth element of that. And now I take this to be the set of all elements L comma I for I strictly less than L and greater than or equal to 1. Okay. This looks like a horrendous thing to do. But anyway, this is the loop, and then at the end you return G. In reality, you want to make it minimal probably, but that's it. Sorry, this is union S, you're right. You want to either append it or sort them or whatever. So let's just think about this algorithm. The basic idea is I have a set G, and I'm going through and I'm essentially making sure that every pair of elements has a remainder 0. Once it's the case that they're all equal to 0, then this tells me that I've got the whole Groebner basis. Yeah?
Where did this index L come from?
So at this point, let's suppose, so at this point, G is equal to G1, and I guess it's an ordered thing, G1 to GL minus 1, say. Okay, so at the first thing, that will be equal to R plus 1. And so I'm just naming it the next one. That's all it is.
L is the current length of this.
Yeah. If I didn't want to use indices, I could just say this would be H comma all the previous elements of G. Maybe that would have been a better way to write it. But so think about this for a bit. Okay. So we're doing this, we're taking the remainder. If we have this, then we add lots more work to do. So my fellow grad student, who was the one that actually showed me these algorithms a long time ago, he sort of had rediscovered all this stuff. He likened it to using a snowblower in Toronto. Yeah.
Yeah, the order of repair, when you define S, like I is less than J, there you L greater. Like, does the order count? Does it matter?
You mean Li and L?
Yeah, I mean, does it matter?
It does not matter. I just actually I always put the largest one. You're right. Okay, let's just make it I greater than J greater than or equal to 1, strictly less than that. Okay, just to keep it consistent. Okay, I typically there's a reason why I want the largest one first, but it's not obvious or necessary at this point. It'll just make our life slightly easier later on. Okay, so first of all, before I go on to the snowblower thing, so does this actually terminate? So this is the whole algorithm. So question, does this terminate? So what do you have here? So I'm going to say I have x to the alpha 1 up to x to the alpha r. That's some monomial ideal I start with, right? And then after I add the next one, I'm adding, if h is non-zero, that's a new monomial that's not inside of here. So this is contained in an x alpha 1 to x alpha r, comma x to the alpha r plus 1. Okay, that would be the first lead monomial of that first h that we reduce. And now I come through, I take another one, maybe a bunch of them reduce to 0, I don't care. But eventually, if one of them still reduces, that's going to be contained in the next set, x alpha 1 up to x to the alpha r plus 2. And if you think about it, if this doesn't ever finish, this is an ascending chain of non-equal ideals. So these are all not equal, not equal, not equal. And so R Noetherian implies that this terminates. In other words, at some point, once we have, it can't go on forever. We don't have any clue how far it'll go. Actually, we have some clue, but we haven't thought about that yet here. Eventually all of those things will start reducing to 0. So this is the algorithm. You could see several problems with it right off the bat. One of them is, I haven't told you what order to remove things from S. Second of all, it turns out that you don't need all of these pairs at all. You can get by with a lot less. We'll see somehow before too long how that'll work. But it doesn't matter. You can do this. Now you might have, if you know anything about Groebner bases, you know there are these like algorithms like F4 and stuff like that. But in reality, it's exactly this algorithm, except that instead of removing one element, you remove a huge number of elements and you choose which ones, and then you somehow use linear algebra to reduce all of those. So it's the same algorithm, it's just an implementation detail in that, if you think of it that way. The good implementation detail speeds things way up, but nonetheless, that's what that is. So does this make sense to everyone? Have we got the notation correct? I mean, so basically the thing is, you have all these things, you have all these pairs, you just take a couple of them, you try to find a new lead term. If you succeed, then you add it to the Groebner basis. If you get 0 remainder, then you didn't succeed and you go on. Yeah?
So every time I just add an element to S. Like when you say IJ remove the element from S,
So there I'm removing one element from S, okay? And here, if I happen to be in the h not equal to 0 part, I'm adding a whole lot of elements.
the IJ still.
Yeah, the IJ is removed. So when it says remove it, it's that IJ be some element of S and S is equal to S minus that element.
Like I remove it because I already checked it.
Yeah.
Okay.
So that's right. So you can remove that. So so if you think about it, okay, it terminate because the actual number of generators of the lead monomial ideal has to be finite. I mean, it can't go on forever. And this is the snowblower thing. So what happens? You know, you have a whole driveway to snowblow. So normally what you would do is you would take the little attachment thing and you would turn it to its side and let all the snow go this way. In this algorithm, you're doing not that. You're moving it forward and just putting the snowblower, it goes in front of you and it just can get larger and larger. But eventually you're at the end of the driveway and you're done. If you can, yep.
H getting smaller.
No, it can get, yeah, but the S poly of it is going in higher degree. In fact, actually, this is probably a good time to show you an example of this. I had it on the last week's set. So so let's see if I can. I have to get onto Zoom to do this, I think. Am I on? Okay, oh, it is being recorded. Good. I forgot all about that. Okay, now I have to. Whoops, wait a second. Okay, good. Okay, you can hear me over there. So actually, no, I thought I had my audio off, sorry. Okay, and now I am going to share this screen. Oops, where is it? Hey, oops, that's way too, wait, why is it so small over there? I thought I just shared this particular window. Is anyone else on Zoom?
There is a way to share.
Yeah. Here, let me see what, oh, I think I hit the wrong button. Then again, maybe not. Okay, I'm going to share again. I'm going to hit this window, share it. I see, it's just because of all the other stuff up on there. Okay, let me make this larger. So here is the example I want to show. I'm going to take a random ideal in 6 variables. And I will explain, I explained to a couple people last time, but this thing here is choosing a random ideal of 4 quadrics in 6 variables. Okay, so in fact, let me, so if I show you, that was called I. So I underscore star, and then I do net list of that. I have a, actually, I get, these are the beginnings of the 4 polynomials, okay? And now the way Macaulay 2 works is that the monomial order is done on a per ring basis. So when you define a ring, you create the monomial order. And that is the default, since we didn't give one. Here's how we defined it, this thing right here. The default is the graded reverse Lex order, because that's typically what you want. Okay. By the way, the codimension is 4 in 6 variables. So in affine 6-dimensional space, this is defining the 2-dimensional thing. And by the way, the Hilbert series of this is that, remember that we did the rational function of the Hilbert series is this, and then I can divide by as many 1 minus t's as I want, which is this reduced Hilbert, and I get something similar. Okay, that is really irrelevant here. What I want to do is I want to do the Groebner basis of this thing, though. So I want to now look at the Groebner basis, and how many elements are there? So notice that I started with 4 things of degree 2. And even though the remainders are becoming less in the order, they're sort of less in the order. They can be in higher degree, so they're actually not completely less in the order. So so in fact here you get something all the way to degree 5. Okay. Now and in fact if I take the source, Groebner basis is a matrix, the degrees of it, sorry, the source of it is a matrix. It is a free module, and this is what the degrees are. And tallying all those degrees, this says that there are 4 things of degree 2, 4 things of degree 3, 3 in degree 4, and 1 in degree 5. Okay, so that's that. Now what I want to do is I want to do the same thing in a different monomial order, the lexicographic order. So here is my my line. All this says, you can't see it here, is monomial order gets lex. That's and then that's that. And now I substitute my ideal into this new ring, which I have to do if I want to do it. And now again, how does this work? This time I'm going to use the F4 strategy that I was just mentioning, because in this case that turns out to be a good idea. And it's done. If you don't do that, it takes about 30 seconds or something like that. Depends on which algorithm you use. And now what I want to do is I'm going to just tally the degrees again, just to see what degrees. So if you think about it, the way once we know more about elimination and how it works with algebraic geometry, we have 4 quadrics. There's going to have to be a polynomial in there of degree 2 to the 4th. It's a sort of Bezout theorem bound, 2 to the 4th, which is 16. So we expect things of degree at least 16. Whoa. So here's what we get. So we have 4 things in degree 2. That's what we started with. And then all of a sudden, here's degree 16, there's 8 things in there, and it goes all the way up to degree 89. Okay. That is very interesting. Okay, you might think, oh, this makes this completely awful monomial order to use. And that's true. But it's also not true, because what's the reason it's so bad is it's encoding information that's very complicated. And so there's a lot more information encoded in a lexicographic Groebner basis than in the graded reverse lex one. But you pay for it. So typically you don't care about the kind of information that it's including. We can talk later about what it's including. There's a lot of open questions about what it's really including. Okay. So anyway, that's an example of it. And this one, notice, look at it. It had 1 all the way up. So at some point, there's only 1 S pair actually left, and you think, I've only got 1 left to do. And each time that you do it, it goes through, and then it adds a whole ton more. Only 1 of those is going to reduce to non-zero. And then you say, okay, and then you do it again. Only 1 of those will reduce to non-zero. And that happens for about 80 degrees or 70 degrees or something like that. Yeah. It depends on what you are interested in. So actually, that's a good question. We could do it over the rationals, but in fact, it would not finish. Okay.
Why is that?
Because if I do random polynomials, then by the time I get to degree 89, almost certainly the coefficients are going to be just ginormous. And so it doesn't really matter about what algorithm you use. It's the answer is going to have these huge polynomials.
Because you're only doing. Why are you doing it? Is it?
So first of all, that's actually an interesting question. The question is, what are you interested in? Sometimes you are interested over a finite field. You are not necessarily interested always over the rationals. However, if you were doing anything analytic or sometimes even geometric or whatever, where you actually want solutions over the rationals or over the reals, then you do want that. And you will not get the right answer. I mean, you will not get an answer that will help you out there. But you will at the same time. So anything that depends numerically on like if I look at the degree of this, that will almost certainly be the same as the degree of the one over the rationals.
So if you did like 32,000.
32,003, it's going to be exactly the same. It will be not different at all. But it could be different. You know, there could be some prime, there will be a handful of primes where it will differ. In fact, it will be quite a few maybe. Yep. Yes. So if you want over in algebraic geometry land, you have a base which is the integers, and over all primes, if I do it over the integers, for instance, then only the ones where the lead term is divisible by some prime is that one going to go away. So then so it's going to be for almost all primes, you're going to get the reduced Groebner basis. And that is because there's only a finite number of numbers appearing in a Groebner basis. So away from any of the primes that divide any of those, you will have it. That's a little vague at the moment because we haven't actually talked about over the integers and things like that. But anyway, so let's see, what time is it now? It is, yeah, it's 11. I need to do just a little bit more before we break. Because if we're going to do the problems, some of the problems. By the way, did anyone look online to see if the problems made it? Otherwise, I will have to post them. Okay. So what I want to do is talk about a couple different where did we end? Right here, I guess. So I'm going to come over here. A couple applications. There's some really basic applications, which we will talk about a little later because I really want to do the elimination order ones. And we'll just do this. Yeah, so I'm going to talk about elimination of variables. Okay, now. Okay, so this is still all in Cox, Little, and O'Shea, right? So we'll be leaving there before too long. But the problem might be the following. Given an ideal I contained in R, which is our polynomial, right? And actually, this makes sense in other situations as well. So you should always be thinking about how would you generalize any of these topics. But anyway, so I want to compute. So let's actually say it differently. And an integer I. Which is going to be in the range 1 to n. I want to compute I intersect k. I want to eliminate. I want all the elements of I that don't involve the first I variables. So that's going to be xi plus 1, xn. It's hard to imagine how this is like completely extremely general, really cool thing, but this is. Okay. There's lots of ways of using this, but we want to find an algorithm for doing this. So here's the way to do it. So so do you all understand the idea? So suppose I have just an ideal in x, y, and z, and I want to find a polynomial in just y and z that is a combination of those things. They want all the ones you have in hand might all involve x, but I want to somehow eliminate it so that I don't have any x's. I want to find elements in there that don't have any x in it whatsoever. And I might want to get rid of a bunch of them. That's what the I is here. Okay, so so here's a definition. A monomial. So actually, what I just said tells you what you should probably do. A Groebner basis is going to uncover things. It's going to remove things. So if I have all my polynomials with x's in it first, then eventually later on it won't have any x's in it. The first variable, and so it will help to uncover those things. Whereas graded reverse Lex will not do that. But I'm going to say that this is a monomial order, a global monomial order greater than is said to eliminate or be an elimination order on where it eliminates the first I variables if whenever the lead monomial of f. Okay, this doesn't have anything to do with I. This is just on its own. Okay, so if whenever lead monomial of f is in this subring, in other words, it itself does not involve any of these variables. Okay, then in fact, f is in the subring too. For most polynomial orders, that just doesn't make any sense. Like for instance, if y is the lead term, y plus x squared, y is in the subring of just the without the x, but y plus x squared is not. So anyway, this is this. So what are some examples? The main one is this is equal to Lex, where x1 is greater than ... is greater than x. There are others though too, but I think I'm going to avoid those for the moment. Okay, because I just want to get enough going so that we can talk about this. Oops. Okay, so here is so theorem. So proposition. If this is a monomial order that eliminates x1 to xi. And G equals, I'll write it as G1 up to GS is a Groebner basis of I with respect to this order. Okay. So I have some ideal, and now I have a Groebner basis of it. We happen to know that that generates this. So let's say it's a reduced Groebner basis. I don't think I need that. But let's say it's a reduced Groebner basis. That's what I have written down. And then G, so this is a finite set. So intersecting it is pretty easy. It's just a check on each one. So if then G intersect K of xi plus 1 to xn. That's what we're looking for up here, is the intersection with that thing. This is just a finite subset of these. In fact, we can tell which ones it is because it's the ones where the lead term doesn't involve x1 to xi. Okay, then this thing is a Groebner basis for I intersect K of xi plus 1 in the induced order on this K of xi plus 1. Remember, this is just any monomial inside of here is inside of the larger one as well. So I just use that to compare it. So it's the same thing. And therefore, this set here, let's call this G prime. And let's call this I prime here. Therefore, G prime is a Groebner basis. Oh, wait. Yeah, G prime is a Groebner basis for I prime. Therefore, G prime generates I prime, which is I intersect K of xi plus 1. Okay. There's a whole lot of uses for this. And on the problems, there's a bunch. I was going to show you one or two, but I think I'm going to leave it and we're going to sort of have fun with that after the break. So it's now just a little after 11, so 11:07. Let's meet back at 11:25, I think, and we'll spend a little bit of time on this. And I can help you get started on a couple of them also, if you want.
Can I ask a quick question?
Sure.
This last proposition you've written, does the reverse direction work maybe under certain circumstances or something? You get a Groebner basis in fewer variables, you can lift it up.
Ah, that's an interesting question. That's tough. Okay. To go the other direction is there could be huge numbers of polynomials here, G1 through GS. And when you restrict to this, there could be very, very few of them. So it's actually hard to do that. You might be able to say something about it. There is this whole problem of taking something in lower number of variables and you want to lift it to an ideal in what higher number of variables that it is flat or it has some property in it. And that's a very interesting problem that is that we can attack with these things. Not that there's good solutions necessarily, but we can at least have some attack on it. This, by the way, I should probably this is the proof of this is as almost as easy as what we did for the number of the generation, the Groebner basis generating it. Anyway, so let's leave it at that for the moment and take a little break, and then we'll have fun on some of the problems after that, and then we'll do yet one more sort of slightly small, shorter lecture at the end. Okay, I'm also going to try to I'm going to try to be a little more precise about my notation. I got a little lax today on it, so I'm not happy about that. Yeah. Are you taking off or? Oh, did I have a good weekend? Oh, I thought you said have a good weekend. And wait, it's Monday. Yeah. Yeah, I had a pretty low key weekend. I just, I walked around a bunch and, just, did some math and stuff like that. Some, but not a whole lot. At first it was kind of cold at the beginning, but then it got better towards the, so.
You've been to the art gallery?
What?
Been to that? The art gallery? Art gallery?
No, I haven't. I need to figure out places to go. I wanted to do some of these with when my wife gets here, but I should. I want to go to is it the Royal Ontario Museum? I haven't been to that.
Yeah.
And I have been up CN Tower before or something like that. But years ago,
We should,
like 20 years ago.
take it to, some theater.
Yeah, that's actually a good
Three or
idea.
four theaters here.
Yeah. Right where I'm living, they're playing right down the road. They're doing Moulin Rouge. And I don't know if that's a good theater or not, but that's on Victoria Street downtown.
Yeah, it's legitimate.
That is a good.
Well, there's Royal Alps.
Oh, yeah.
It's like 3 or 4.
Yeah, okay.
Yeah, a question on the culture. It's not related, but
Oh, okay, sure.
so I have a problem with the sorting thing. So I would like to sort something like this
Yep.
in a way that like is
And that takes a little bit of computation, but not so much. I guess it could take a lot. But generally it's pretty straightforward.
You said you posted something, like, do you have a, like, not using their.
Not Moodle, it's just on the, if you go to the Fields Institute. We get started. So should we take a look at one of the problems a little bit to get going on it? I think the problem involving, let's see, which problems did I give? Where are my problems here? Oh, shoot. Okay, so on the problems sheet that I gave, the first one was the one we just did. Okay, so you have the code there that you can play around with that for doing the Groebner basis and Lex and reverse Lex. It's already somewhat of an open problem to describe the lexicographic Groebner basis for a set of random polynomials of a given degrees. And the fact that it goes up to degree 89 is just staggeringly bad. So, but anyway, that's an interesting thing. Problem 2 is maybe a good one to get started on, and problem 3A is probably a good one to start on first. Okay. So I'm going to write down what the problem is up here. Are people online here? Okay.
Yeah, all good.
Okay. So here the problem is you have Q adjoining some things, Q root 2, root 3, root 5, I think. This is a field, right? So I want to know, and then I'm taking, what is the element that I'm taking? I didn't name it, but let's say that alpha is equal to root 2 plus root 3 plus root 5. And I want the minimal polynomial of this. This might not be the best way to do it, but you can use Groebner bases to do this. Okay. So how do you do it? You guys want to think about it for a bit, and then we can discuss it a little bit, because but I think this is a good one to start on. But you should be thinking Groebner bases, and you should be thinking of elimination ideals that we were just doing. Those are the hints I'll give.
I'd rather, take three variables. It's fine. Square root is 2, y squared is 3, z squared equals 5.
Yeah.
And then, you look at the idea of generating by x plus y plus e.
Well, actually, you have an ideal with more generators than that. Because you're in Q adjoin X, Y, Z, or Q adjoin the variable names you're using for these three things. So you have those polynomials also. So if they're A, B, and C, say, you have a squared minus 2. So that's going to be an element in your ideal.
But to get the minimal polynomial,
Right.
I'm just interested in a plus b plus c.
Yeah, but how are you going to get the minimal polynomial? But that is actually, that's right. So if we name these things, if this is A, this is B, and this is C, then this is just A plus B plus C, and we want the minimal polynomial.
So this was part of the exercise, but you have to figure out what's the relationship between the minimal polynomial. and Some idea.
Yeah, a little bit, and we can discuss it all together. But if people get stuck on it, then we'll just talk a little bit more about it. Okay. But you should think of it as in a polynomial ring in a handful of variables, basically.
So you could like build it.
So if I set alpha is equal to that, and that's one of my variables, and then that hopefully will be in my ideal that I have.
This is specifically what the middle.
So
Because
if you want, I can tell you more. But so are you people online trying this as well?
really. But this is the theory of this.
Oh, I see. It says, can you please repeat the questions that are being asked? I hate it when people don't do that. I will try very hard to do that. Oh, yeah. Sorry about that.
No, it's a good sign of
And then we're going to do it in Macaulay too, but you have to sort of figure out what one wants to do on it first a little bit. Sorry.
Yeah, we have to figure out. Well, no, we're trying to. I get that. This adjoint equals data. I don't know. No, the This is all
Yes.
So, sorry, I have no idea what I'm doing. This is all I know. I know if you quotient by the middle polynomial, it's isomorphic to this guy.
That's right.
So I presume this is the ideal that we kind of maybe want to look.
Well, actually, you want an ideal in, you have to bring these variables into it as well. So, so as a slight hint here, the way I would think of it is, what is, if I call these things A, B, and C, I can really think of this as Q adjoin here. That's not going to work, is it? Q adjoin A, B, C. Okay. And then modulo, and then what's the equation for A? It's A squared minus 2, right? And then B squared minus 3, C squared minus 5. So that thing is actually essentially this. But, and this is an element in there, which is A plus B plus C.
So you're sorry, you're saying that this guy's isomorphic to that quotient?
The field here
Yeah.
is actually isomorphic to this guy. Does that make sense? In any case, even if you don't think it's isomorphic, I want an element here, A over Q, where A squared is equal to 2. And that is that element. It might be the negative of it too, but and so these three things might be part of the ideal that I'm going to do. But this doesn't bring into being this element. So how do you do that? Does this make sense? Does anybody need any assistance?
Right, so this, we don't, but we just like.
You're trying the linear algebra approach, right? So yeah, so I want to try to use Groebner bases and elimination ideals.
Yes.
So the question is, how do you do that? But as I said, this is not really the way to do it. Probably the linear algebra way is probably better. But this gives you an idea of ways you can attack. You can use Groebner bases to get at things that aren't obvious at first.
I mean, you can take the various powers of alpha. And you'll get.
Yeah, you'll get elements of this, right? Yeah. So that would be one way to do it.
Yeah, like, not quite seeing how to phrase it in terms of Groebner basis, but the way you would do this is. You would look at all the powers of it.
Yeah, I know.
Then you want to say, now you're gonna get three equations. Alpha squared, alpha cubed.
Actually, it's more than that because this thing is a basis over Q is 8-dimensional. This is 8-dimensional over Q.
Right, so you get, yeah, so you get like square root of. 6 or 10s or about 15. Is it intentional?
Yeah, it's mostly because it's
So it'd be like, so you have 2 to the power 3, that's
Oh.
just 3,
I think
3 surds.
so you wanna like take the element out of this.
Yeah, but that's cheating.
it's one way. So wait, are you guys
Good, but it might have to be in bracket.
do you have it or do you want some more hint here? Do you want more of a hint? Maybe this is
Yes.
so do you see that if I have A, B, and if I call these things A, B, and C, I could really think of that as A squared minus 2, it will be in my ideal. I'm setting that to be 0 somehow. But now I need this one in there somehow. So why don't I use a new variable called T or something like that and set it to be the sum of these things? So for instance, if I consider these, and now I take T minus A plus B plus C. That kind of encodes all the information that we have, if I call that element T. And the question is if I want to eliminate variables, what does that mean here? What?
Oh.
I just did you come up with this or?
In that area.
Yeah, okay. How are you guys doing? Oh, you got this one already. Yeah, okay. We'll figure out the exact polynomial by computer. We certainly can't do it by hand. You what?
We have get on like a. Figure out.
It's just the first element and you
Oh,
couldn't get.
yeah, that's right.
So it's flat, but that's.
Oh, yeah. Actually, if you just yeah, that's right. I can show you how to do it. So to get an element of a matrix, you do underscore and all matrices. Okay, so underscore is indexing, not brackets, and everything is 0 indexed. So that's the normally the 1 entry of the matrix. So it's the 0 entry of the matrix. So it's this thing
Yeah, that's why I tried-
O12 underscore 0.
That's what we tried up here. I think it's probably something like you have to save it in something it's not like.
Oh, I see. Yeah, actually, this is some of the peculiarities of the syntax of Macaulay 2 is that this will bind closer with I than with
Oh, is it
this.
trying to do Groebner basis of the. entry
Of
instead
the I underscore 0.
If I just put number brackets around it.
If you put parentheses around Groebner basis of I and then underscore 0, it will give you it will maybe give you the element. It might give you a vector, but I think but you can also do underscore parentheses 0, 0, close parentheses to get the actual entry. Should we go through this by computer yet, or are you
Second one, I guess it's what we do is this. These two and then. It's the same program. They made them.
so which one did you guys move on to after that?
3D. What it, you get a T by it.
Oh, okay.
Should we also complete the probability?
That one might need one more thing that we haven't quite done yet.
Okay.
So it's on.
It has to do with saturation, so that you have to do an ideal quotient, I think, which we haven't quite done yet. So, two A and B are good. Although two B, you can't do by hand so easily.
No, because we want to close it right on it. So, no, you just want to if the log is populated, yeah, it is. Okay. No, just pass it to another direct. Oh, yes.
Okay.
So how would I annotate what you did on Jets? Yeah, I forgot that. That's always pretty big, that I feel sorry yet.
The Groebner basis is big?
But that is, it's hard to see.
What do you think?
Because of the,
They,
these are the same.
oh, it is the polynomial you want.
Okay, that's the minimum one. Yeah.
Okay, I'm not gonna write down that, I can give the list.
Trace only involves the fact that it became like a physical fact. Most of the eight, right, that could be our. How do you see that? Section, formal, yeah. So this is. By the, yeah, the rationals, order. Yeah, that's the generators of first, so just from that, and this first one only. But that is also extremely, I like the kind of. I mean, there's one in the Z, which is like not. Yeah, this one. Right? How did you get?
Request. When I have to go to basis and I want to intersect. How I can do that, like practically like a red. If I want to do by hand.
Do what by hand?
Yeah.
Yeah.
So when I have the group of basis there was already a polynomial, we didn't have any other variable.
Yeah, so then, when you do an elimination, you like one, the first one, another, there's or. The last area, the third. So like. That's one of the processes, so your full big time, like, it's parents or.
And if not,
It's not.
okay.
There are cases, right, where you do the elimination order and it doesn't get down to single pair.
No, that's right. It doesn't have to. It does here because it's a zero-dimensional thing. But in fact, otherwise it won't usually. I mean, it could. There can always be a polynomial that involves less variables.
I want to do the variable that I don't want to eliminate as force.
Yeah, you want it like that. Okay, it tries. Get rid of it, or each one, and then the thing that we add is small.
This should just, okay.
Well, the part of your, I think I missed the first part of your explanation, so it's like. This, okay.
Exactly. So this allows you to do lots of computation with fields without having to think of it as fields. You just um, well, I mean, you have to know something about it, otherwise it's an abstract problem. Yeah. So so that's right. So in fact, if I just give you any elements that are algebraic over Q, and I give you their minimal their relation on it, and I do this process, it'll find me the minimal polynomial of the sum. Yeah, I know. That's why part of why I gave this problem. So it's so anyone else? So you guys are all past that, right? Or yeah. Yeah, okay. I could show how easily to do it in Macaulay 2 as well, if you want, but maybe you've all done that already. But there's also an eliminate command in Macaulay 2. So if you do eliminate, make this ideal, and you do eliminate I comma the list ABC, it will give it to you without having to go through and compute the Groebner basis. But behind the scenes, that's what it's doing. Did you want to? Do you want to see the thing? I'll put it up over here. Oops, that means I have to get back online. If anyone else is interested in seeing the solution, I'll just sort of go through it a bit, or people can help me do it. Wait. Where's the Zoom?
I could just call it like, I guess.
Okay. Now I'm going to share my screen. Okay, so can you see that? Does anybody want to sort of tell me what to type for doing this problem?
Yeah.
Okay, so are there? So do you want to see it? Anyone want to see it? You already seen it. Okay, so here is the here it is over there. Can you see that? Oh, you got it. Okay. So the first thing is you make a polynomial ring. Does that, and maybe someone else should explain it instead. Or do you want me to explain it? I'll explain it. Okay, so you make a polynomial ring in the variables A, B, and C, and T, where T is going to be this guy down here. So that's just that. And I'm making a Lex monomial order because I'm going to want to get rid of the variables A, B, and C. And so then I make this ideal here, which is exactly the one that was pointed out there. A squared minus 2, B squared minus 3, C squared minus 5, and T minus the sum of the ABC. And now I'm going to compute the Groebner basis of this because I'm in the right monomial order to do that. And so actually I can't really see that. So here is the Groebner basis. Oops. Okay. So I made an ideal of the Groebner basis by doing ideal of it. And then I do an ideal underscore star. And then this netlist just put these boxes around it so it's a little easier to see. Actually, I have a little routine that I use. But if you see, this is now the Groebner basis of the ideal. And this one only involves T. So that is going to be the minimal polynomial. You have to convince yourself perhaps that it's actually the minimal polynomial, not just a multiple of the minimal polynomial. But in fact, in this case, it is the minimal polynomial.
Okay.
No, it doesn't matter. If it's it actually that was a mistake I put on that. You can do elimination for any Groebner basis. Yeah, yeah.
If in our case, we didn't have a polynomial that was only instead of intersection with empty.
That's right. The empty, it won't be empty, it'll be the zero. So that is certainly a possibility that it intersects the zero.
That's a bad. That is not something that's only the bottom.
I'm sorry, what?
And that does not depend.
No, that's right. By the way, this tells you a little bit more if you look at this thing. Like it tells you that C can be written linearly in terms of T. So in fact, the field generated by that T is exactly the same as A, B, and C because there's A, B, and C written in terms of it. Can you see it? So this thing here is saying C is equal to 1 over 576 times all of this stuff. Just kind of amazingly awful. Okay, so here are the commands that I used. Well, I restarted and then I made a polynomial ring. A, B, C, T, and then monomial order is Lex. And then I made an ideal, just sort of the way you would think you would make the ideal. And then there's this Groebner basis command. This gives you a matrix of a one-row matrix of all the Groebner basis elements. And so ideal makes it into an ideal. In other words, it's just as an ideal in Macaulay 2 isn't just the abstract ideal. Every ideal comes with a set of generators also. So so in some ways, even though I say it's the ideal and then I look at it, I'm really getting the Groebner basis. It's not trying to muck around with it in any way. If I did min gens of it or something, it would change that. And then this net list is just a little thing that takes a list. So GBI underscore star, any ideal underscore star gives me the list of all the entries, all the elements. So that would be one way to get around using this this underscore zero thing that you guys were doing. And then net list of a list just gives you this kind of nice blocked display. That's all. You don't have to do that. I kind of like it. Another way to do it is just to take this ideal I, doesn't have to be in any particular monomial order whatsoever, and just call the eliminate command I on the variables ABC. If I do that, it just comes out, it takes the one element in there that was in the subring of the remaining variables.
So what is your setup? Are you using the Emacs or something?
Oh yeah, so in Emacs I have a so that's actually a useful thing that I have is that I have I'm running Macaulay 2 in Emacs and I have a .m2 file. In this case, it's called week2 problems.m2. And then if I'm in the M2 file and I type F11 on a line, it sends it to the other thing. You can do this also in VS Code, but it's a little less convenient, but it's pretty good if you prefer VS Code. We had Macaulay 2 running in Jupyter Notebook, but it kind of got messed up with when Jupyter Notebooks got updated, and so the version of Ubuntu did not get updated. So if you have Linux, you can run Jupyter Notebooks with Macaulay 2, but on the Mac you cannot. And we're hoping to fix that. There are going to be a few other sort of internal Macaulay 2 people coming in a couple weeks, so maybe we can fix that.
I asked you this. This would be done like a Python wrapper.
Oh, you did talk about that, and there are people working on such things. I could put you into contact with them if you're interested.
Python wrapper.
So suppose you want to call Macaulay 2 from Python, or yeah, you can do it via Sage. But if you're not using Sage, you can also do it. But it's a little bit of a hack at the moment, so you have to do some work.
So you use it in Sage, but is it like integrated? Like, is it callable from Python in Sage, or is it just another package? Sage.
Yeah.
The Sage is like,
Sort of, yeah. So a lot of times, these days you don't really need all of Sage or in fact, it's even bad in the sense that it redefines certain things so that it makes it hard to interuse with some Python things. Maybe, although I think it's always possible. But yeah, it would be good to have that
there
one.
is like a symbolic package.
Yeah, that's
It renders things.
yeah, that's right. You were saying that. Computationally, SymPy is pretty not good.
No. That kind of calls out like native libraries are.
Uh-huh.
That's really what Python is good for. It's calling it to.
Right. Did anyone try doing any of the other ones that we were just talking about?
Anyways, that's very cool.
Yeah, like, we're just like.
Yeah, so it's kind of cool that you can do all of this, all this stuff in field theory really is just about ideals in this kind of setting, if you want.
And so when you enter the command eliminate I and then gave it A, B, C.
Huh?
So are there any restrictions on what you can eliminate?
If it's in a polynomial ring, no, you can put any of the variables in the polynomial ring. But you can't just say eliminate A plus B plus C or something like that. It has to be variables that you're eliminating.
Eliminating them implies that they can be defined in terms of the remaining variables. So
Well, I mean, so when you eliminate some variables, you're keeping the rest of the variables. So there are two ways that you could actually say this. You could say, give me all the polynomials in I that only involve these variables, or eliminate these variables and give me it's the same thing. But in fact, in Macaulay 2, you say it in terms of which ones you want to eliminate, not which ones you want to keep. There's no reason why you couldn't write a program to do that. I mean, a little function.
So what is the output of eliminate? Is it another ideal?
Yeah. So like, for instance, here, it's an ideal in the same ring, but where you've taken I intersect K of T here, Q of T. And that's an ideal. And then you just think of it as an ideal in your current ring. So it's really, this is coming out in a ring with variables A, B, C, and T, but it's not using A, B, and C.
But this ideal.
Does that make sense? I don't know if that helps. Any questions online, by the way? Oops, I don't know if you can hear me. Actually, you should be able to.
guess. I and and after
Actually, you don't even need to delete the T. Wait, problem 1 is the radical ideal one, right? Yeah. So so if I take I and I add TF minus 1, then really what you're doing in terms of this stuff, you're thinking you're adding T is really 1 over F somehow. Well, maybe we don't think of it that way. So instead, suppose that F to some power is in the ideal. Okay. Well, then if you've added TF minus 1 into the ideal, then T to the N, F to the N minus 1 is also in the ideal. So 1 is in the ideal. So all you have to do is check. You just have to add TF minus 1 and see if 1 is in the ideal.
Okay, so you.
Sorry, what? Are you talking to me or? Oh, yeah, that's right. So beta is equal to that. So one way to do it would be to multiply through by alpha 1 plus alpha 2. And then you have some equation on it. But it might be that you also have to do what's called saturate. You want to know that alpha 1 plus alpha 2 is invertible. I think here it is actually. So I think that you don't have any trouble. I think it will just work. Should we try it and see? So tell me what to type here. So what is our ring here?
Guess we need 3 variables for the alpha 1, alpha 2 data.
So, okay, so let's call those X, Y, and Z or something like that. Wait, do we have 3 variables? We have alpha, beta, alpha 1, alpha 2, and beta. And those are the only variables we have, okay? So let's do A1, A2, and B, okay? And we'll use the eliminate command later. Let's just do this for the moment. We can put in a monomial order. And now what's the ideal that I want to consider here? Actually, let's not call them A1 and A2. Let's call them X and Y. And let's call this one, let's call that one Z, okay? So what is X, what's the equation for X? Okay. Y squared minus Y. Y squared minus 5, oh yeah, 5, right? And then what is the last one? X times Y minus 1, like that.
No, it's +1 inside the brackets.
Actually, something's wrong. Maybe I didn't run this line. Yeah, okay. Okay, so now I have this ideal. Now what do I do? What are we trying to show?
Want to eliminate, I guess, X and Y ones and then eliminate Z ones.
So should we do the eliminate command? Is that okay? Or do you want to do it by Groebner basics?
Eliminate.
Of I, and which ones do we want to eliminate? Maybe X and Y. So here's the equation that other thing satisfies. But that's actually not quite the question that we were trying to ask, right? So what is it? We're trying to show that these things are equal. So what we really want to show here is that, so which way is it? Which way is it? One of these two things is obvious, right? And one inclusion is obvious. Which one is it? Beta is certainly in the field Q of alpha 1, alpha 2. So we want to show that alpha 1 and alpha 2 can be written in terms of beta. Okay, so we want to well, or actually maybe we want to eliminate first alpha 1 and then alpha 2. So like for instance, if I just eliminate X, okay, so Y is alpha 2, right? So I'm not eliminating alpha 2. So I'm keeping alpha 1 and beta. And here what I have is Z is beta, right? Wait a second, this isn't working. Maybe I do have to do the saturation. Let me just look for a second. Saturated divide X plus Y. No, that is not necessary. I didn't think it was. Okay. So wait, so what we want to do is write X in terms of Z, right? So, so can we do that? Actually, I thought we could. Do I have a mistake in here? Here, let's do a Groebner basis. Let's do X then Y then Z and do monomial order. I thought I did this one to check it out. Hope it's right. And now if I do GBI is equal to Groebner basis of Groebner basis of I. And now I do net list of that kind. So what is this? Neat list? Net list? Oh, yeah. Let's make an ideal of it. And let's see what this tells us. This actually tells us a lot. So this is the Groebner basis for X, Y, and Z, and this is that part B of the problem. So what does it tell us? Yeah, exactly. So if that came out to be Y, some like no polynomial like it, or Y squared is in there, then that would tell you that it would be actually probably, if it was Y squared, it would be a degree 2 extension to add Y. So it wouldn't be in Q of Z of that beta. Oh, here, sorry. So see the second one, it's some large constant times Y is a polynomial in Z. And the reason this works is this is returning a reduced Groebner basis. If it wasn't, it might be hard to see that. Should we start in on more stuff, or is this more fun? So one thing I do recommend, and because we haven't really done it yet, and I think it's really good to think through this stuff. I would do problem, oops, where is it? Problem 4. Okay. Problem 4 is a theoretical one, but it's using elimination. How can you compute all of these notions that we've just got here? And we were doing field theory stuff here, and these are going to be a little different. And so, by the way, there's no class next week because of the apprenticeship program. But the next class after that, we will probably talk about some of these. So it's worth it to think about it. If you need hints, this stuff is probably all in Cox, Little, and O'Shea. Okay. Yes. Sorry. Yes. Like what kind of thing? Underscore is the indexing operator, and then if it's a matrix, you do underscore with parentheses. 0, would give you the first entry of it. You can also flatten, and you can take and make a list of lists of it and stuff like that. Lists will print double, with this thing. Online, all these things will print a little bit, on the Melbourne server. It has a slightly better display, maybe. What are you looking for? I can't actually hear you, sorry. Can you just grab the whole session, you mean, and copy it? In Emacs you can, in VS Code you can. I mean, how are you doing it in terms of a terminal? Oh, really? It should just run with Ubuntu on Emacs. That's interesting. Ah, WSL. Oh, yeah. Yeah. No, that's a little more complicated because the question is whether the Emacs is inside of WSL or outside of it. There are two ways of doing it, and I don't actually have a.
Inside WSL, but then you have to use something to put a lot of it.
Actually, I'd be interested in hearing how to do that at some point. Yeah. Okay.
But here, come on, give me something.
Yeah. Yes.
So I created like a range.
Just.
Does this make sense?
Yeah.
But you know, I tried to access the variable 0, 0, gives me an error.
It's X_00.
But I mean, if you create,
Do you have Emacs installed on?
I do, but I think you create
One second, I'm just gonna save this.
you do it just with one variable. I did try that.
Yeah, no, that's true. Because R_ an integer gives you the that integer, that
Okay.
variable. But so if I do R_0, I would get this one,
Oh, I
R_9 or 8, I think the last one, or
I see,
something
I
like
see,
that.
I see.
So so you probably want to just use X_.
X_ there, I see.
In programming, the R_ is actually pretty good, but. Okay, should we start doing other stuff now? Or are you doing well with this stuff? You want to continue? Which do you prefer? Let's do here, let me get out of this and let's talk again. Okay, anyway, so some of these problems, it's trickery to figure out what you're almost in problem 4, every single one of these things, you're going to add some new variables or a variable, and then you're going to compute the Groebner basis with respect to an elimination order and then get it. And if you haven't seen it before, it takes a little bit of thinking. For some of them, using that thinking that t times f minus 1 is a good thing to consider. But for instance, for intersection, that's not going to be quite it. So you have to think about it. Okay. Okay, so let's get started again. It looks like it is recording. Okay, so hopefully, so you figured out so Groebner basic, they might not be the fastest thing, but it's kind of cool sometimes that you can do all of these different things that are related to other subjects that, like the field theory, which is kind of cool. And online, I'm going to try hard when there's questions to repeat the question. So I understand that whenever I watch a YouTube video of someone giving a lecture and it doesn't happen, it's really annoying. So I don't want to be that annoying person. So I think there's a lot more I would like to say about the elimination order, but I think instead I'm going to let you do those problems and figure it out yourself. I think that'll be better. What I really want to do is for the rest of this time, we're not going to quite get through all of it. It's going to be computing syzygies. And free resolution. So elimination orders are really good. They do all sorts of cool things for you, but this is a different kind of application of Groebner bases that is really cool. Now I'm going to define syzygy and stuff like this. So just so we're all coming from the same place. So here's the situation. For this part of it, for the definitions of it, R is just some ring. R equals a commutative ring. Maybe even Noetherian, but whatever. It doesn't have to be for this. And we're going to let F1 to Fr be elements of R. Okay. And then the syzygy module of these elements of F1 to FR. So I'm thinking of this as maybe the ideal of these, but I have actual specific elements in mind. The syzygy module of this is the set of columns G1 to GR such that that well, let me just write this. Sum of FIGI the G1 F1 plus plus GR FR is 0. And this is sitting inside of the ring, the free module R, capital R to the little r. Okay. And as I've mentioned in the past, it's an awesome word, but this thing really gives you a display of the ideal in some ways, oftentimes. Sometimes it's a huge mess. So, but it's a pretty good thing. Now, if you think about it, this is really, if I just take the map from R to the little r, mapping to R, given by this matrix, this is the kernel of that map. That's all it is, linear algebra. So let's actually define slightly more now. So if A is an M by R matrix over the ring R. Okay. And so what we think of is that, I'm going to think of A as F1, F2, up to FR are the columns. And each Fi is in R to the R, right? But I'm just writing it. And this is exactly what I was teaching in my linear algebra class a few weeks ago, in my undergrad linear algebra class, except that it was over field rather than over ring. So this is this, and then I can consider the corresponding homomorphism. And then we have, do I want to name it? I could just call it A. I think I will. We have R to the R to R to the M given by A. And the way I think about it is it takes a G1 to GR. Oops, was I using brackets? I want to just be sort of consistent. This is just setting it to the product, right? And then the kernel of A is called the Syzygy module. Of A. Okay, it's exactly the same as that, but that's a one row matrix. Okay, so this basically then Syzygy modules are just the kernels of maps. I do. So this R, this is M rows, so it's an M here. Thank you. Do I have all the rest of them right? I hope so. Okay, so anyway, so this is this thing, and here's a definition that we will use. So we let Sys of A denote some matrix or any matrix. It's going to be a function. Given A, it's going to return you a matrix, a specific one, but you don't have it, but it's not going to be given very nicely. So let's see how this goes. Denote a matrix such that the image of Sys of A. So let me get the so denote here. I want to state this slightly differently. Let's do it like I have in my notes. Denote some R by P matrix. So R is the same R, and now the number of columns is some new number. Some R by P matrix such that the image of Sys of A, the image of it will be sitting inside of, so the way I think about it is Sys of A is now a map from R to the P to R to the R. Okay. And so the image of the Syzygy map, I want to equal the kernel of A. So this is going to be our programmatic way of computing syzygies. If I want the syzygies, I will do this, and this just means the columns generate. So so let's do an example. So here we're going to take, okay, here, okay, Macaulay 2 likes to put arrows going the opposite direction, okay? And I'm going to do that here. So I'm going to take an example, R, and this is going to be the matrix F1, F2, F3, where F1, R is going to equal K adjoin A, B, C, D. This is my canonical example. This is the twisted cubic curve, okay? F1 is going to equal C squared minus BD. F2 is going to equal BC minus AD. And F3 is going to equal B squared minus AC. Okay, so I have this map from here to here. And then I want the kernel is going to be sitting inside of here. What is the kernel, by the way, of this? What are the relations on this? So I want the vector of 3 polynomials that dot to 0 with this thing, basically. So actually, if you think about it, let's try one out. If I take A times this guy, I have an AC squared, right? And here I have an AC. I want an AC squared, so I'm going to put a C here, and the signs cancel. So if I take A times this one, the C squared term will cancel with this. How about the ABD? Well, I need ABD is from here, and I need it to have a different sign. So minus ABD minus ABC. So I would like to claim that this thing here is a syzygy. Syzygy is just an element of the syzygy module. So A minus BC here. And if I check this out, I think everything cancels if I got it right. So I can, if I want the kernel of it, I'm going to have a matrix where each column will be a bunch of generators of for that. And then in that case, the image will be the span of, the R span, the module generated by all those guys. So that's one of them. How about any others? Well, how about B times this one? BC squared, and here's a BC squared, so that should be a C, but it has to be a negative sign here. And then I have a B squared D, and here's a B squared, so maybe if I put a D here, they'll have different signs. So that's another example. And I'm pretty sure that's one. A minus BC, B minus C, D. And lo and behold, that's it. This is the image of this. This is Sys of A. This is A. This is Sys of A. And the kernel of this is equal to the image of this. So this is an exact sequence and at this point here. Okay. So we're going to talk about how to calculate the syzygies of this thing. It's essentially Groebner bases. And it's a really cool thing. I already told you about Hilbert, how he had some elimination theory method of doing it that I was tasked to as an undergrad to implement, which I failed miserably. Well, it just didn't work in practice. Then when I was in grad school, my friend Dave Beyer refigured this kind of stuff out, and I got really excited because I'd been wanting to be able to compute syzygies, and so this is it. it is not completely clear that this is everything. Okay, the way I did it as an undergrad, we did it degree by degree and did it by linear algebra essentially. Okay, and calculated a bunch of syzygies. How do you know you had it all? What we used was the Buchberger-Eisenbud, what makes a complex exact theorem, which we might talk about at some point. Yep. This is not a regular sequence here. What? This is it's just not a regular sequence. So it's in fact it has it's the max length of a maximum regular sequence inside of this ideal generated by this thing is 2. So not 3. Otherwise you would get what's called the Kazul complex, this way. So anyway, so this thing here is this is a free resolution. So so let's actually just define that. So free resolutions. I'm not sure that I'm kind of at this weird spot because not everyone knows it here, but a lot of people know it quite well. So I'm trying to catch some middle ground. But if I but it's a little tricky. So I don't want to just assume all these things. So let's actually just define it. So suppose M is a module over a ring R, e.g. M is equal to R modulo I. So for instance here, I could do one more step here. If I take the image of this is ideal and I do this, this is a whole exact sequence right here. So if M is equal to R mod I, well, I don't care. M is some module, and suppose that 0, M, and now we have these F0 to F1. These are all going to be free modules like those guys. F2 might not end though. Suppose that this is exact, is A exact, and B, each Fi is a free module. Then this part here, F, then F is called the free resolution or a free resolution. Of M. Okay. This thing is probably the bread and butter computation. Groebner bases are kind of really bread and butter for lots of things, but for many, many things in algebraic geometry, they all start from this kind of computation. And actually a lot of things in commutative algebra as well. So we want to be able to compute these things. Any question about my definition? If I left out some thing like I've been leaving out all day, it seems. Okay. By the way, if there is one other thing, if M is graded, e.g. I contained in R is homogeneous, and M is equal to R mod I. Then what we could do is we could put a grading on all these free modules, just put those twist of minus D's that we had last time and make it into a graded exact sequence. So then we often suppose each F sub I is equal to a direct sum of R with some twist of degrees minus Dij's over some set J here, like this. And each map, oops, did I name the maps? I did not name the maps. These are called these delta 1, delta 2, delta 3, etc. This one is just, F0 is just a map on the generators to M. So we often suppose that we have that and that each each delta I is homogeneous or graded of degree 0. In other words, it takes elements of a given degree to the same degree, okay? And so as an example of this is the twisted cubic example up there. 0 goes to the example above. This is going to be R mod I. No, it did, yeah, R. And now we have 3 generators mapping to F1, F2, and F3 are all quadratic generators. So these are going to be R to the -2, and there's 3 of them. And now what is then I have an R2 for the 2 Syzygies. What are their degrees? There's 2, they're both the same degree. What's the degree of those things? Is it, there are 2 options, -1 here or a -3 here. But it's sort of cumulative, so it goes up to -3 like this. Okay. So if this is not something that you're familiar with, you might need to ask me about this afterwards. But yeah,
Sorry, what's the D?
that's like 2 or 3. It's just some numbers.
Oh.
For some degrees, D, I, J. In this case, they're in Z, but if it were graded by some other group, then they would be in something else. Now, here, the reason I'm bringing this up is the other thing that we really want to compute is the Betty table of R mod I, or of the resolution of R mod I. Okay, so what is that? So that's a description of all these degrees. And the way it works is you take the homological degree. So this is going to be in step 0, 1, 2, etc. So I'm going to write 0, 1, and 2 as these numbers are not part of it. This is just to help me index it right at the moment. And then I take the degrees. The lowest degree is going to be 0 here, but it could be negative if and so on. And then 1, 2. And then here I'm just putting the Betty numbers, which are the ranks of these things, in the right spots. So here this is an R. So this is going to give me a 1 here, and there's nothing here and here. So this R is this, and so this is like the homological degree I and some degree J. Okay. So no, let's leave that out because that's not that doesn't match what I just did. Here though, where does this sit? This says we have 3 generators of degree 2. One option would be to save this 2, put 3 down here. But that turns out to be kind of a mess because then the things just go down very far. So instead, what we do is this is degree 2 off of this. So we just we go 1 over and then down 2, or 1 here and over 2, and we put a 3 here. So this 3 means this is R minus 2 to the 3. If there were cubic generators, they would be down here and so on and so forth. And then in this next row, this one here is in degree, there are 2 of them, so it's going to be a 2 somewhere. But the way it works is every time you go over or down, it increases the degree by 1. These are in degree 2. We want to get to degree 3. That's just over by 1, and so we have this here. Okay, so one could actually say very specifically a definition of this thing, but I'm not going to do that right at the moment. So you can do this. And in Macaulay 2, this is oftentimes what you really want. This information gives you pretty much everything that you want. That's not true, but a lot of the numerical information about the ideal.
So what do you mean?
So R of -2 is a free module of rank 1 that is exactly R, but it's got a new grading. So this is equal to R, except that the generator of this is a degree 0, and except that R in degree -2 in any degree D is really R in degree D. So what this means is that this thing here has its generator. Here the generator is degree D. This has its generator in degree D, in degree 2 in this case. So -2 is generator in degree 2. Yes, thank you. So you're taking sub D here is, no, that's not right. Over here. Okay. It's just a shift. You're taking the same module, you're just shifting over the degrees, and whether you shift right or left is the definition, and Sarah chose this for us, okay? So that's what we have. And so you can take this information and then just display it like this. This turns out to be a more than just, there's the whole theorems of Boyce-Soderberg that deal with these things as you think of this as a vector space. And so I don't know, that's pretty cool. Not all free resolutions are kind of nice and finite like this. Here's another example. Suppose R is k of x mod x squared. And we take we're going to take k as the module. Well, what is the module k as an R module? All it really is R modulo the ideal x. Okay. So as an R module, it's just R mod x, and that therefore has a generator R mapping down to that, and the kernel is the ideal that defines it as x. So that would be x to here, like that. What's the kernel of this map?
Sorry, can somebody switch the
Well,
video? We can't see.
Oh, sorry. Okay, sorry about that. Thanks. Okay, so here we have R is k of x mod x squared, and then we have this, and we have this map R to R. So this is now exact at this point. So what's the kernel of this thing? What? It's another copy. It's generated by x. So the kernel of it is just the ideal x, which is also the image of x, and consequently, this is infinite. So this is pretty wild that this very simple one is infinite, and any complicated one over the polynomial ring is finite. That's Hilbert's theorem, and you can prove that using Groebner bases, which I will probably put on one of the homeworks later on. What's our timing here? Yeah, I want to give you an idea of how to compute syzygies using Groebner bases. Okay, once we see this example, I think that you can generalize it to actually prove it yourself. And I think it'll be easier than seeing the big general thing with all this stuff. So how to compute syzygies? So let's do an example. By the way, once we can compute syzygies, as long as we can compute syzygies of an arbitrary matrix of between two free modules, then what we can do is we can do just what we did there. We calculate that one, and now we calculate the syzygy of the next one, and we just keep going until we're either get tired or it becomes zero. Okay, and so here, what I'm going to do though first now is try to describe a little bit this kind of example over here. And I hope I'm using exactly the same example. So I'm going to consider the example above. And I hope I did it right. Yeah, good. Okay. So F1, I'm actually going to call it G1 now, because this is going to be part of our Groebner basis. Is going to be C squared minus BD. F2, G2 will equal BC minus AD. G3 is equal to BC, B squared minus AC. What's the monomial order that works here? This has to be, I want these to be the lead terms, okay? So it's not going to be our usual ones, A is greater than B or anything like that, because if we have that, almost certainly these things will be maybe be larger. So I'm going to choose B is greater than C is greater than A is greater than D, and then I'm going to choose Grevlex inside of this setting, although I don't think we need really to know that much about it. Okay, so I'm essentially permuting my variables, and then I'm going to look at the highest. When I compare, I'm going to look at the lowest power of B will go out first. So C squared is larger than BD, and here it's the lowest power of B. Yeah. So these two have, this has the lowest power of B, and then the lowest power of C. So this is out front, and same with this. Okay, so it turns out this is a Groebner basis. How do we tell? Well, we do S pairs. So let's do a couple of the S pairs. There's 3 S pairs between these things that we have to do. I'm only going to do 2 of them. The third one will turn out not to be necessary. So here is one of them. In fact, I'm only going to do one of them probably. So let's take S poly of G1 and G2. Except I'm going to do G2 and G1. This is that, remember, it didn't matter. It's only up to a sign whether you put the I before the J or J before the I. But I really want it to be like this. And so what is this polynomial? Well, that if it's really going to be the thing that knocks these two into each other. So it's going to be B times this and C times this and subtracted. So it's going to be C times G2 minus B times G1. Okay, is everyone okay with that? I'm just writing it like this. Now, if this is really a Groebner basis, this thing here, after I write it all out, will have to reduce to 0. It will have remainder 0 with respect to these 3 polynomials. So in fact, what is the remainder of S poly of G2, G1 with respect to G? G1, G2, G3, say? Rem, that's an open parenthesis, and an open parenthesis, a close parenthesis. Okay, now what is this? That's equal to C times G2 minus B times G1. What is C times G2? It's C times this, and then that one is B minus B times that. I'm adding, and then I'm getting, what am I getting? What is this equal to? Sorry, what is it? It's equal to B times G3. So if the remainder then, sorry, D. Okay, so what we get is that C times G2 minus B times G1, and now we subtract off D times G3. This is minus DG3 here. Is I'm really writing that? And that's equal to 0 if we multiply it out. But if I don't multiply it out, I'm getting that this is equal to 0. This is a syzygy on G1, G2, and G3. Okay? This is very, very cool. So that means that every time I take a pair of these things, that will give me the first 2. And if it is a Groebner basis, I can keep subtracting off things. That'll be each something times a G sub I. You know, in fact, we already have from the division theorem what it will be roughly. And that's going to give us a combination of, if we don't write out what the G1, G2, and G3 are, that this is a syzygy. You got that? So that's one of them. And the other one, by the way, that should be one of those guys there, right? C times G2, it's negative of that second one, okay? And similarly, if we take S poly of G2 and G3, G3 and G2 say, what is that going to be? That's going to be C times G3 minus B times G2. And what is the last one? I think we have to add A times G1 and we get 0. Okay. So for every single S pair, we get a syzygy on these generators. But now take a look. This is the first element that we had here, and this is the first element we had here. I could, if I don't multiply the GIs out, I can think of this as an element in the free module R to the 3 in this case. Does that make sense? So, and this one also is an R to the 3, which is good because that's where these syzygies are supposed to be living. And I get a whole bunch of these. And Frank Schreier noticed, and he wasn't the only one that noticed, but I think he noticed it in this exact setting. So each remainder of a S polynomial of a G, J, and a GI with respect to G gives rise to a syzygy. Oops, sorry. Thank you. Okay, so here we are. So each one of these things in a general situation gives rise to a syzygy or an element in R to the R if G is equal to F1 to F or G1 to GR. Okay, so we get a whole bunch of elements in here. Now, suppose that we can do Groebner bases in this thing here. So now we have to define Groebner bases in the free module. Part of the R. So we need to do this. Okay. But let's suppose that R to the R is equal, I don't want to give notation for it yet. But what do I want my elements in R to the R to look like? I want this to be, each of these things to be monomials. So this is going to be like a basis element now inside of there. So then I have a bunch of work I have to do here. I have to figure out what the monomials are inside of R to the R. Those are going to be easy. It's x to the alpha times a basis element here. I have to figure out what a monomial order is here. Well, we have to actually think about what monomial orders will work. And then we have we can just run through everything else we've done. And we have the notion of Groebner basis. Okay, so anyway, we have this. And then the theorem is that in a specific monomial order on that R to the R, these guys are going to be a Groebner basis of the syzygy module. And because we know that Groebner bases generate the ideal that they're Groebner bases of, they're going to be actually a generating set of syzygies. So this step one, these are the steps that we still have to do. Steps one, we have to define them in here. Step two is we have to define a specific order. On R to the R, a monomial order on R to the R, such that these guys are the lead terms. This one here and this one here are the lead terms. And this is called the Schreier order, or the induced order. We'll have to define that. And then third, we have to prove that these syzygies up here, we give rise to a syzygy here, that the star syzygies give a Groebner basis of, they're all syzygies, and they're all in R to the R, and they're, so we can look at their Groebner basis or whatever. They are a Groebner basis of the syzygy module of the kernel of A. The kernel of the G1 to GR. How many ever of them we had? R, I guess. Okay. So what's our timing? We actually do not have much timing for this. So, but if you think about it, so what is the monomial order going to be? How do I get this to be larger than these things here? We have to really do this in a little bit more detail. So I actually want to do this out because it's kind of important. But basically, if I just replace, if I look at the lead term of G2 and the lead term of G1, and I just replace, now this is not useful. Sorry. Let me think about how I want to end this stuff today. So, so we do have these three things to do. This is an easy thing to do. Okay. The specific monomial order, we will be led by our nose to just have those things turn out to be the lead terms. And then to prove that those give a Groebner basis is a little bit of work, but actually it's quite straightforward at that point. And it's really cool that it's a Groebner basis. If I just choose an arbitrary monomial order on this R to the R and I take a Groebner basis of it, it's just huge compared to the number of the actual generators. Whereas this is at least giving some sort of reasonable number oftentimes. For the last few minutes, let's do a couple Macaulay 2 resolution calculations so you see how to do that. Okay. Oops, I have to get. Okay, looks like I might be on. I've got everything turned off. Okay, let's again share this. Okay. Now let me put it in here. So let's take an ideal. So I'm going to take a polynomial ring. We could do it over the rationals over a finite field. This doesn't really matter. Let's do it in 4 variables for starters. I'll just use A, B, C, and D. Okay. And I'm going to use a function called monomial curve ideal to just give me quickly an ideal that's a little less trivial. Okay, so this is an ideal that is the image of this is actually the rational quartic curve in 3 space. And it has generated by 1 quadric and then 3 cubic equations. And now I can do C is equal to the resolution of I. There's an interesting problem in computation in commutative algebra. If you've ever studied much commutative algebra, you know that sometimes when you say the word I, it means the ring mod, the ideal. And that has been carried over so that Macaulay 2 has that kind of thing also. So when you do res of I, and let's not do that at first. R to the 1 mod I, okay? So there is a free resolution. So let's take a look at it. Can you see that at all, or should I make it larger? What? Yeah, I know. So here are the 4 generators, BC minus AD, and then 3 cubics. And then each of these columns is a syzygy that you can check is a syzygy. But these things have a relationship on them as well. So and what is a syzygy on these? It's going to be some sequence of 4 things that dots the 0 with the columns. So for instance, D times the first column minus C times the second column minus B times the third column plus A times the fourth column is 0. Okay, and then there's only one of those, and then it ends at that point. We can also do Betty of C, and this gives us the display that we were mentioning. So the 0, 1, 2, 3 and the 0, 1, 2 are the various degree indices. This is homological degree, and these are actuals. I think of them as slanted degrees, but the entry here is the number of elements at that homological degree of the degree, which is the sum of the two numbers. So this one here, there's one quadratic polynomial in the ideal, that's 1 plus 1, and there were 3 cubics, which is 2 plus 1. And there were 4 linear syzygies off of those quadratics, so that's that means it's linear off of this 3, and then there was 1 linear syzygy off of that, which is the one here. So this is the Betty table of that kind of thing. It's kind of here's another kind of example. By the way, once you have these numbers in here, you can compute you have a different algorithm for computing the Hilbert polynomial and Hilbert function and Hilbert series of an ideal. So I'll let you think about that. Maybe I'll put that on as well. And in fact, that was how Hilbert first wanted to do it, was first compute these things and then do it. I don't know how he could possibly ever compute with these things at the time, but he somehow he did pretty good. Okay, so here's another example, and then we'll call it quits. Let's do a ring. I'm just going to do it over a finite field because I like finite fields. We're going to take the 18 variables. Okay, so if I do gens of R, I see A through R are the variables. Okay, I'm going to take a generic matrix in R, starting with the variable A and a 3 by 3 matrix. Okay, and M2 is equal to a generic matrix. It's bad. It shouldn't do that. I understand. This is a conversation that we've had on Git. That this is one of this comes from the original Macaulay thing from the 80s, and it would actually be hard to change that because enough code uses those things. So it would be really quite tedious to do. Anyway, suppose we do this, and those are our two ideals, M1 and M2. Now I'm going to take, in this case, it doesn't really matter whether they're one way or the other. I'm going to take the commuting matrices. So M1 times M2 minus M2 times M1. I'm going to flatten that matrix. Actually, I'm going to just take ideal of that matrix, which is the ideal of all entries. And this ideal is a whole bunch of quadratic polynomials and 18 variables. There are 9 of these equations, but really only 8 because the trace of AB and trace of BA are the same thing. And now, so for instance, if I do codimension of J, I get 6. Degree of J, 31, whatever. What about a free resolution of J? This is the resolution of the quotient, and this is it. And here's the Betty diagram of it. There are 8 quadratic generators. Turns out there are 2 linear syzygies on these things, and then 31 quadratic syzygies, and then it gets kind of a little more complicated. It's still completely unknown what these things, these must represent something. So one thing that Eisenbud did, by the way, you can take a look at some of these matrices. So if I do C.dd underscore 3, no, that's a bad one. How about underscore 4? Okay, well, it's a little hard to see here. If I make it really small, even there, I can't really see. Never mind. Okay, but in any case, one thing Eisenbud mentioned a long time ago, when you still use printouts rather than screens to view things, he said, anytime you have a specific display of a free resolution, there's a theorem in there staring you in the face, waiting to come out. And I think that's actually still true. I think there's still lots of theorems still available to get at. In fact, some of this latest work of Jerzy Weyman and crowd is is based on trying to do that in a really systematic manner. Anyway, this is all for now. Today was slightly, I felt a little disjointed because I was trying to I was going to not at the right pace for everyone. So so you should let me know what you think about the pace and stuff like that. And next time, what we're going to do is we're going to I think, well, we might spend a little time doing some of the answers, having some people present answers for some of the problems. And especially that problem with how to compute all those things. And then I want to really talk about computing with modules. And right now, I guess I do want to do this at some point as well, because it's really cool. And but also, it turns out there's only a handful of building blocks you really need to compute with modules, all the homological algebra of it. And that will allow us to get, just without even thinking about it in terms of Groebner bases, just thinking about it in terms of these handful of things, it will allow us to really really move on and up our level as to what we can compute and what we can construct. So anyway, that's all for now. Thanks. See you guys actually in 2 weeks. And this week I'm going to be gone here. Next week I'll be around. So I'm plenty happy to talk to people if you have questions or want to discuss more of the material as it is. But this week I'll be gone. Okay, thanks.